welcome and good morning, good afternoon, or good evening, depending on wherever you are on the face of the earth. This is the fourth panel organized as part of the CAD for Assurance initiative, and we are excited to have such a wonderful panel on such an important topic. And the topic is securing crypto in the pre and post quantum era, opportunities and challenges. As I said, we have a really distinguished set of panelists and a distinguished moderator. We'll learn more about them and I will hear from them. And of course, we will also hear from you, your questions and your remarks as you go along. This is actually an 80-minute panel. It will start right now after this welcome remark. So Debdeep, can you go to the next slide? So I'll quickly talk about this CAD for Assurance initiative. It started October 2020, right in the middle of the pandemic, and it's led by the hardware security community. The whole idea was to bring together the open source CAD tools, benchmarks, metrics, and some of the publications related to this overall idea of assurance of hardware, particularly focusing on the security and the trust issues of hardware. And we have seen tremendous response from the community. As you can see here in this slide, we have 56 different CAD tools on assurance. We have more than 1,000 benchmarks on different topics and many other contained in the cadforassurance.org website. If you have not visited that yet, I will strongly encourage that you visit it, and hopefully you will find the content very useful. As I said, the whole idea was to bring together the academic community and make sure these open source tools and benchmarks and metrics are usable by the broader community and they can benefit from that. So till now, we have 80,000 unique visitors and more than 28,000 page views. As you see, these numbers are definitely very, very encouraging. In parallel to developing the website, the community also wanted to have a group of or a set of webinars on the tools, particularly focusing on tool demos, as well as a set of virtual panels on some of the important topics in the field of hardware security and hardware assurance. And with that goal in mind, we have been diligently working together to bring to you a good number of tool demos and webinars. So far, we have given 16 different tool demos and webinars, and all of those recordings are available in the IEEE CEDA website as well as the CAD for Assurance website. So feel free to look into those if you have missed those webinars. We also have brought to you 3 different virtual panels in 2021 on some of the really exciting topics. Except for one, you have the recording for 2 of the virtual panels available in the website, in the IEEE CEDA website. Feel free to, again, look at them. And we have got tremendous response, again, in terms of attending these webinars and tool demos and panels. We have more than 1,200 total registrations and more than 1,000 attendees. And we are pleased to have support from IEEE CEDA, IEEE Hardware Security Technical Committee, and also several major companies, as you can see the names here. And the tool webinars and panels are organized by myself, Professor Gang Ku, Professor Sung-Yi Ho, and Professor Ye Jin. Next slide. I quickly would like to acknowledge the organizational sponsor as well as the technical sponsor for this event. Let's move on. Next slide. So there are a number of activities going on, and today we are doing the panel 4, as you can see here, today, June 10, and we have a number of other activities coming up. I would ask you to look at the website, particularly the panel 5, which is coming up in 2 months from now, and then a few more tool demos. If you're interested to contribute to this activity, to this initiative, please feel free to do that. There are ways to contribute in the website. If you can go to the website, you can see the link. And then finally, for panel 5, it's also a very important topic. If you're interested, you can register right now. With that, I will hand over to Dr. Ye Jin to introduce the panel moderator. Here. Here, can you introduce the moderator now? So it looks like Year's mic is not working. Debdeep, do you want to take over?
Sure. So first of all, I would like to say that thanks to IEEE CEDA and also the HSTDC for inviting us for this wonderful panel. And I'm fortunate to have, like an elite group of panelists. So just to quickly introduce, I would like to introduce Professor Ingrid Verbauwhede. So she's a professor at COSIC and KU Leuven, Belgium. And she's a pioneer in the field and needs no introduction, but I will still kind of do a bit of formality. She's a member of the Royal Flemish Academy of Belgium for Science and the Arts since 2011 and is a fellow of IEEE, fellow of ISCR for pioneering and sustained contributions for cryptographic hardware and embedded systems. She is also kind of the co-author of this book on lattice-based public key cryptography, and her team is also one of the designers of Saber, which is in the finalists of the NIST post-quantum portfolio. To introduce Ro, as we call him, Rosario Cammarota. So he's a principal engineer at Intel Labs, where he leads the effort on privacy-enabled and computing and cryptographic technologies. Ro's research is at the intersection between cryptography and computing, focusing on fully homomorphic encryptions, secure multi-party computations, and their applications to AI and statistics. Ro is one of the technical advisory board members at SRC, where he contributes to developing research programs in hardware security and AI hardware. Moving on, Professor Ramesh Karri is a well-known figure and again needs no introduction. So he's a professor at electrical and computer engineering at NYU Polytechnic School of Engineering at USA, or Tandon School of Engineering. And he is a co-founder of the Trust Hub Embedded Security Challenge and NYU CRISP Center. He's a researcher who is specialized in trustworthy hardware, high assurance nanoscale integrated circuits, architectures and systems, and is one of the faculty leaders of the world's most comprehensive student-led cybersecurity program called CISO. Professor Karri is an IEEE fellow for his contributions and leadership in trustworthy electronic hardware. Moving on, we also have another distinguished guest among us, Dr. Apostol Vassilev, who is a research team lead in the security testing, validation, and measurement group at NIST. And at NIST, he is an active participant in several national and international cryptographic standard groups. Dr. Vassilev works closely with academia, industry, and government, and he's a chairman of the government industry working group dedicated to modernizing crypto validations. We also have, among us, Dr. Sri Parameswaran, who is a professor in the School of Computer Science and Engineering at University of New South Wales in Australia. And he served as the program director for computer engineering. So Sri Parameswaran is served as an editor in in the IEEE Embedded System Letters, and has been in the editorial board and program committee of several flagship conferences. And he brings in us the expertise of low power systems, high level systems, and networks on chip. So I would like to kind of welcome all the panelists and just to quickly introduce today's topic. We all know that cryptography has...
Hey, Debdeep, can you hear me?
Yeah, I can hear you.
Okay, good. Finally, you can hear me. So I mean, before you move on, I really want to introduce you because you, sorry for my bad internet connection. So
no worries.
Professor Debdeep is currently, I mean, he has a very long and I would say very impressive background. I would only highlight some key parts, which I think are very, very important. So first, Professor Debdeep is visiting at KU Leuven under the ASEM DUO fellowship. He's currently a professor at the Department of CSCIT Kharagpur. And he is the recipient of the prestigious Shanti Swarup Bhatnagar Award 2021 for science and technology. This is the highest science honor in India below age of 45. And he is a fellow of the Indian National Academy of Engineers. So that's something that I really want to highlight. Debdeep.
So thanks here for this kind introduction. And so I really would like to thank all the fellow speakers for kindly, accepting our invitation. Moving on to introduce this topic, we all know that cryptography has evolved from, from art to science to, to the world when we were more concerned about provable security. And with the emergence of several applications, technological and business solutions, it's really a kind of, I would say, a boom. So, and at the same time, there has been several emerging applications where we are constantly, outsourcing our data and processing our data on remote clouds. And that makes security so very important, security and privacy in particular. However, I mean, while there are several techniques, in particular, fully homomorphic encryptions and other methodologies which are trying to constantly secure our data, the problem often comes when we try to translate this theory to actual practices, and when we want to really deploy them on real systems, either software, hardware, or even firmware devices. The pain often comes from the fact that often these models or formal security models are not good enough to capture implementation level attacks. And we know of a plethora of various kinds of microarchitectural attacks like Spectre and Meltdown and so on, which has really crippled these implementations when we talk about security. When we talk about classical AES, we have found out things like side channel attacks, fault attacks, which have really kind of, hurt the crypto devices. And there are so many crypto devices which are, kind of day in and day out getting affected by these kind of attack vectors. Moving on, I mean, when we have this world of public key cryptography, which inherently requires mathematical structures, we also have the loom of quantum computers, which tries to kind of bring in, completely kind of remove the security of certain public key crypto devices or systems. On the other hand, right, there are certain crypto devices which or crypto assumptions on which we can still base our public key crypto algorithms in the post-quantum world. And that brings us to this very important effort from NIST to standardize the post-quantum world. But while there are, while on one hand, the algorithm designers essentially are kind of shortlisting the standards, we also have to think about their implementation security. So the question could be like whether these designs or their implementations are still vulnerable to side channel attacks, fault attacks, or bring something more. Do we have enough amount of CAD tools or necessary tools to kind of secure our systems? And how secure are our FHE protected data, which are often also reliant on such kind of post-quantum assumptions? Are they really safe in such kind of adversarial scenarios? So we look forward to our panelists to find out answers. So before we kind of move on to more open-ended design, we would also like to kind of listen to some kind of position statements from the panelists. So I would first of all request Professor Ingrid to kind of give us an opening remark on this topic, and then we will have a quick round of kind of comments from each of the panelists. So Professor Ingrid, if you may kindly start sharing your views.
Thank you, Professor Debdeep, for inviting me on this panel. Also, I think I'm really impressed. I mean, I should say it's nice that people organize this, see that moves in this direction, and I see so many people online. When I started hardware security, there was not even an NSF panel to submit your proposals to when you were working on hardware security. Although I have to say, my very first proposal, the title was VLSI Design Methodologies for Hardware Security, because there was a panel or an NSF call on EDA topics. So I had to fit my research somewhere. So I think over the years, what I've seen is that the technology, I mean, the effort doesn't change. What changes is the mathematics we have to implement. So these days we try to implement post-quantum crypto because the mathematicians have figured out that those algorithms resist attacks from quantum computers. The challenges there are similar to the challenges we had many years ago, but then for different kind of algorithms, means that the first thing we always look at is performance. Can we get this thing implemented? And the second thing is, can we make it side channel secure? There is, and I think that's an important role for CIDA, there is a huge room for design automation in this field. And that's especially that's on testing, but especially on making and supporting designers in making all these implementations side channel secure and attack resistant. And this is not just for the current post-quantum or the future whatever homomorphic encryption schemes, but it's for all existing crypto hardware. So it's extremely difficult to estimate security at design time. And that's, I think, something which is beyond post-quantum is estimating security at design time. What makes it tougher for post-quantum is that, yes, we are now looking at masking schemes for post-quantum. And this masking, we realize that masking is expensive. Masking is expensive for post-quantum. And that's a topic which we are working on here. It's first of all, it's expensive because we need mix and match of what's called arithmetic masking and Boolean masking. It's also expensive because it requires huge amount of randomness, another topic which we need to work on quality random number generators. And the third thing is it's very difficult to evaluate. So this is now very labor intensive measurements in the lab, trying to figure out where the thing leaks. So I think there's lots of room for EDA here. That's my initial statement. I hope I started something. Thank you, Debbie.
Thanks, Professor Ingrid. I mean, so we have a nice blend of, like academia and industry in our panelists. So talking about industry, I would request Ro to kind of make some initial comments.
Yes, and thanks Debdeep, and thanks Ingrid actually for the comprehensive introduction. You touched upon all the important points, in the move to post-quantum and other mechanisms. There are a few things that I would like to touch upon as well, and it's kind of ironic, especially when it comes to post-quantum cryptography based on lattices, right? It's true that from a cryptoanalytic perspective, they are more resistant than previous schemes to advances in computing as computing moves to quantum computing. So it is true. But ironically, these schemes are actually also much more complex. The algorithms that needs to be implemented to realize these schemes are much more complex. And as a result of that, the attack surface to physical attacks is much larger. And so what Ingrid was saying earlier, masking, it becomes really expensive. Yes, because you need to cover a lot of things. More importantly is that automation becomes becomes a must, but it was difficult to do for, let's say, simpler algorithms. And when I'm talking about simpler, I'm talking about much more contained algorithms. Is even more difficult to do to something that like instantiation of post-quantum cryptography to lattices. So that's one thing. So we have ironically a larger attack surface to basically reproduce the same security mechanisms with higher resistance to cryptanalysis, and that's one thing. The second thing, again, because of my bias toward processing encrypted data in my day-to-day world, there is also that even from a cryptoanalytic perspective, that there is something that is not common, for example, to block cipher, and it is actually quite different in lattices. So in block cipher, the fact that you can attack and you can do key extraction using side channels, right, does not weaken the cryptoanalytic strength of the block cipher. It's just that you are using a recording device to add, to record observations and do something out of it. Let's say that you are cheating the cryptoanalysis from this perspective. But for what concerns lattice cryptography, actually, it turns out that even small leakage that may be present it can reduce the complexity of the cryptoanalytical problem, and you can run actually algebraic attacks. So this is something that in the context of side channel does not exist for block cipher. And it is also an objective that you are able to reach in a different context of physical attack, which is fault attacks. So you do exactly that. You try to weaken basically the complexity of the algebraic problem, but you are using an active attack. Now you have a similar situation, but with passive attacks as a consequence of the mathematical structure of your cipher. So there is complexity in implementing secure, securely security mechanisms based on at least lattice cryptography. There is complexity in automating not only the design but also the testing for side channel. And you know, I tend to agree with what Ingrid was saying earlier, that there is a huge opportunity for the computer-aided automation community to continue advancing the field, and there have been like enormous advancement, particularly contributed by academia, but also transferred technologically to industry. But there are also aspects of the deployment conditions that needs to be taken into account. To one of your points, deep in your slides, that might end up to different type of assurance criteria to estimate the risk of compromission as we are moving to post-quantum. So now I described the first transition, right? So we are having the same security mechanisms, bulk encryption, authentication, key exchange, key encapsulation, and whatever, from pre-quantum to post-quantum. From block cipher, we know what to do: increase the keys, the key size. For public key cryptography, we are replacing the public key cryptography with something else. And this something else has some issues in practice that are of a much larger scale. And then there is the second shift that is from classic security mechanism to something new, which is processing encrypted data. And the result of that is that just the complexity in terms of the data types that you are using and other things is increasing, which in part exacerbates the problem of automation. So that's my opening statement. Yeah. Okay. There's a lot of work to do in practice.
Yeah. So thanks. That was, I think, quite interesting, and we'll get back to some of these points subsequently. So I would request Professor Ramesh to also give his statement. I mean, I have his slides, so let me try to quickly see that it's working. So I hope that the screen is visible. So Ramesh, maybe you can quickly, you can have your statement. Yeah.
Thank you, everyone. Thank you for having me on the panel. And as Ingrid pointed out, there seems to be a huge interest in this topic, and thanks for all the folks that are interested on this topic. I am a professor of electrical and computer engineering here at NYU, and I co-founded the NYU Center for Cybersecurity. It was formerly called CRISP. Next slide, please.
Okay.
So what? Yeah, thank you. What I wanted to do is three things. So talk about things, different kinds of threats, a different threat, a different side channel, and the different approach of using that side channel in the context of defense. And I'll clarify what I mean by that. And as Ro pointed out, the complexity, and Ingrid pointed out, the complexity of these systems exposes and expands the attack surface. Algorithm subversion attacks have been there pre-quantum, and they could be much more prominent post-quantum. This is a different threat model than what most of us have considered explicitly. And in fact, this particular attack reflects is a realistic threat model. For those, some of you might be aware of the classical or classic freak attack, where the saboteur was allegedly a nation state actor. You can figure out the acronym from that. They, for example, intentionally weaken the OpenSSL protocols by restricting the size of the RSA export key to below 512 bits or so, some certain number. So this could be decrypted by using the factorization algorithm using modest computing resources. Now, coming to the context of the PQC suite of algorithms that are under development and standardization, the PQC signature, key pair generation, signature generation, and signature verification steps similarly use, for example, common algorithms like for secure hashing and a strong pseudo-random number generator source and so on. So in that context, these ASA attacks can either subvert the, for example, the hash function, silly context example is SHA-3 to SHA-0, or subvert the random number generator, for example, AES-based random number generator to a weaker block cipher-based random number generator. So these are some of the kinds of things that could happen in these kinds of complex algorithm subversion attacks. Next slide, please. Debdeep.
Sorry.
Could you move to
Yeah.
Thank you. So in the context of a different side channel, most of you are look at power timing, EM, and other side channels. So, but one of the more interesting side channels, at least to me, is what we pioneered at NYU in 2011. For that reason, at least, it's based on hardware performance counters that are digital side channels, and these hardware performance counters are special purpose registers built into the performance monitoring units of all processors. HPCs store counts of software and hardware events in the processor. Every HPC provides information about the microarchitectural state and events in the different parts of the processor. For example, an example HPC could include events like number of cache misses, branch mispredictions, instructions committed, and so on. HPC-based monitoring is interesting, or is attractive because it incurs minimal time overhead with zero over hardware cost. Hardware HPC-based monitoring does not require any extra modifications to the monitored code. In fact, about a decade after its introduction, about last year, Intel and Microsoft, Intel came up with the TDT technology, threat detection technology, I guess, and Microsoft uses that technology. TDT is based on HPC monitoring and so on, and Microsoft uses it for ransomware detection and so on. So next slide, please. So if you look at HP, so in the context of PQCs, HPC signature of a PQC code, it doesn't matter which one, denotes the HPC values obtained during the execution. You can use these signatures to fingerprint runtime behavior of a PQC code in many ways. In one way, the time series-based signatures may capture the time-based variations of the HPC values during the execution of the code. For a seed input and a message, seed comes into play because you have lots of random sources in your algorithms. The other thing is something called the program checkpoint-based signatures, which focus on selected locations, because especially these are complex algorithms, so you cannot continually trace all parts. Maybe you want to checkpoint and focus on those parts. And one thing that we noticed is because of the complexity of the algorithms and the inherent randomness in these algorithm implementations, the random generators, random number generators, and so on, this alone may not be sufficient. Just monitoring HPCs passively, is no longer sufficient. So we use what's called gray box fuzz testing to generate high quality seeds high quality message inputs to maximize the coverage, state space coverage of the particular targeted PQC implementation. This way, what you could do is essentially dynamically shape the HPC side channel features. And this is what unlike just leaking secrets, which is the typical application for side channels, here what I'm pointing to is a different application, which is monitoring HPCs to detect threats. Next slide, please. That's my final, last but one slide, I guess. Yeah. So so this is a quick table here. I don't expect you to read this. What we looked at is 3 types of subversions. One is pseudo-random number generation, hash, and varying the security parameters. Then tried this on about 4 or 5 PQCs, standard candidates. With these combination of HPC monitoring and dynamic fuzzing, we were able to get 100% accuracy in detecting if the given code is authentic or trusted or the one that is expected versus if it is subverted. As I said, it's final, but I have a couple of more slides. Quickly, I'll go over that. Next slide, please. So slightly related we accelerated signatures and key encapsulation schemes of the PQC algorithm on FPGAs and ASICs, starting with C-specs. We implemented the 9 NIST round 2 digital signature schemes. Of these, the green ones are the round 3 finalists. The yellow ones are the backups, I guess. I was checking those in the morning earlier today. So security level roughly corresponds to AES 128 strength. Security level 5 corresponds to AES 256 strength. And here, the key takeaway is that the tools are open, the codes are open, and the synthesis, high-level synthesis scripts are open. And you can, I gave you those links. And on the final note, as I pointed out, there are lots of additional side channels that might become more prominent. One example is the subversion attacks, different side channels that could become useful in detection, not as a combination of side channels that could become useful. Multimodal side channel could be an interesting direction. HPCs could be one of those in the pool. And finally, thank you. And I look forward to engaging with the rest of the team and all the participants.
So thanks, Ramesh. And it's amazing how the list of attack vectors increases. And thanks for bringing the performance counters and microarchitecture attacks into our discussion. So with this, I would like to move on to Apostol and would like to kind of request you for your position statement. Apostol?
Yeah, thank you. Can you hear me?
Yeah, we can hear you.
Right. So I'm going to try to reflect in my opening statement some of the topics that Ingrid and Rob brought up earlier, so that we have a sort of a similar set of topics viewed from slightly different angles to kind of make it more interesting or more comprehensive, whatever you want to say. We all agree that many years of research, engineering, hacks, and defenses have shown us that the problem of side channel leakage in hardware is here to stay, and more needs to be done on the 2 fronts of research and engineering to assure a move beyond ad hoc masking of crypto algorithms that is often subjected to empirical, subjective analysis with inconclusive results. In other words, just because someone tests the masking and declares it good does not mean another person with better equipment or skills cannot defeat it. And this has created serious problems for the industry in terms of liability and costs. We all know that NIST is working now to finalize the selection of PQC algorithms and the other panelists talked about it. These are going to be new algorithms based on different kind of math compared to the legacy public key algorithms, lattice and all these things. But our preliminary analysis shows that they too are susceptible to side channel leakage when implemented in hardware. So we need to figure out ways to develop effective and robust masking for them. And similarly, for the class of lightweight crypto algorithms that NIST is looking to standardize, they are primarily intended for hardware. So clearly the challenges in implementing crypto in hardware are growing. I think the only way we can scale up to these challenges is by moving towards more analytical masking techniques that can be analyzed rigorously and put into hardware efficiently and robustly, so that we can have objectively provable and practically effective assurances of security. So a good step in this direction is to perform pre-silicon analysis of side channel resistance of specific masking algorithm, because this approach offers clear benefits in terms of cost, efficiency, and depth of analysis. And so we've been trying to sort of promote research in this area by working with academia, by funding research. And we've seen some exciting progress emerge from it. For instance, some of the work that the Fix Institute in Florida with Professor Kharagpur are doing and other places. At the same time, another interesting line of work here, promising line of work, is a development of robust masking solutions that scale up to arbitrary security orders. And that's an example of that is the work Professor Standard and his team at the University in Leuven, and they're developing security claims that can be analyzed for full implementations, including composability reasoning and thoroughly tested with formal methods. So similarly, the work of Professor Moradi from University of Cologne and others on the design based on secure composable gadgets, and also a possible solution here. These are, in my opinion, very interesting advances that show promise. But to have a real shot at addressing the side channel challenge, we need to do more. And there is one aspect that's critically important for the success of these approaches. The stack of available design and production tool that's used by the semiconductor industry. That transfer essentially the logical netlist into silicon gate layouts on the major hardware platforms of interest, the FPGAs, ASICs, etc. Currently, the major focus of these tools is to optimize for area, power consumption, and throughput. This is all good, but what's missing is taking as constraints the security assumptions of the masking approach expressed in terms of engineering parameters for the gate layout. As a result, we have seen that in many cases, these hardware compilers optimize out some necessary for security constraints, which renders them ineffective. A quick example here might be something like maintaining a specific separation between tiles on the chip or what have you. In a way, what we're seeing today in hardware reminds me of the early days in software security, when a programmer may set a cryptographic key to 0 after it is used to ensure the original value does not linger in memory after it's freed. The compiler will then notice that this variable is not used after it is set, so it would optimize the zeroization out, rendering the protection ineffective. The software industry quickly recognized the problem and introduced mechanisms to instruct the compilers to avoid optimizing security-sensitive code. A similar recognition here is needed for hardware, and the corresponding solution needs to be developed for the hardware domain. Without it, we will not be able to advance much in either of the directions I pointed earlier in terms of pre-silicon and robust masking, theoretically masking techniques. We can only, and we'll, as a result, we'll only go deeper in side channel leakage hell. So in a nutshell, what we need to develop, I think, is theoretically sound masking techniques. And I concede they're expensive, but we should be able to first figure out theoretically sound masking techniques that we can reliably transfer onto silicon, knowing that all the security sensitive parameters or assumptions that are important for theory have been enforced correctly onto the mask. And only then we can think of ways to make side channel resistance verification much more objective and trustworthy, which is currently another big problem for hardware. Again, going back to my first comment, what we have most today is ad hoc masking and some kind of inconclusive side channel analysis. And we need to move beyond that to scale up to the challenge. So thank you, and I look forward to the discussion. That's my statement.
Thanks, Apostol, for making very important comments. I mean, masking is definitely one of our, very coveted design strategies, and one probably also need to look at a combination of attack vectors like side channels and faults, which can be, I think, quite interesting. So with this, I would like to move on to Sri, as we call him. Sri, are you there? So
yes,
for your
yes.
position statement. Yeah.
Thank you. Thank you. So perhaps I'll take a slightly different approach. But thank you very much for inviting me, first of all, and thank you very much for all the other statements. Very, very illuminating in a lot of different and interesting ways. The two algorithms that people talk about in post-quantum that has probably shaken the world are the Grover's algorithm and Shor's algorithm, I guess. And Grover's algorithm essentially says for if I'm not mistaken, to put it in layman's term, for block ciphers or for symmetric cryptography, your keys have to be essentially doubled. So if you normally have a key of 128, A is say 128, with everybody having 10 computers, and if you can break a computer when every a billion keys per second, then you can break it in 67 billion years, and Earth's life is only 10 billion years or something, 13 billion years. So it's never going to happen, kind of. But quantum computers, they can theoretically crack it with the same number of computers in less than a second, in fact, 0.1 second, I think, if my calculation is correct. So it's about 2 to the power 64, it becomes 2 to the power 64. So the easiest thing is to just double the key size and we are safe. And as I think Ro pointed out, it's just double the key and you're fine. But public key cryptography is going to be a problem. And that is where we are, that we have to make certain that we can save these things. But let's really take a look at what quantum computers have where they are right now. In 1982, the idea was floated, or maybe around that time anyway, by Richard Feynman and Yuri Marin. 2000, we had a 7-bit qubit computer. There was a 12-bit in 2006. 2011 had a 14-bit computer. 2017 had 49 bits. 2020 had 65 qubits. Google in between had a 32-qubit computer. And IBM has had a 127-bit quantum computer last November. And they say they're going to have a 433-qubit one this year and a 1,121-qubit one in 2023. Now, the interesting thing is that 2021 computer, 127-qubit for quantum computer is 2%, has a 2% C0 error, which is quite high, very high. To correct it, you probably need another an exponentially greater number of qubits to correct all those errors. In order to completely break the current sort of RSA bits, you probably need about a million qubits. We are very, very far away. So we are not, I don't think the problem at the moment is not too serious yet. It's probably at least another 30 to 40 years away, at least, before we need post-quantum cryptography. But we never know. There might be some amazing change in life, change in things, a change in technology, and then we might actually start doing things that are that might actually necessitate post-quantum cryptography. However, all of the problems that exist now, like acoustic attacks, the DPAs, the fault attacks, the cache attacks, as Ramesh pointed out, and equally the memory, the memcom, the streamcom, the RPA attacks, all of these things are going to be still there, and we're still going to have to sort this out. And as the last speakers pointed out, we need, just like we measure power, just like we measure area, or we need some sort of constraint levels or some sort of levels of measurability of security. Perhaps we can have, I think at the software level, we could possibly have safe libraries and things like that. But at the lower level, perhaps, the simplest thing might be to be able to look at different process corners and look at TVLAs or something like that, the test vector leakage assessment, or something like that for each for different process corners on each of the chips, each of the gates and things like that, and make certain that we have sufficient coverage to make certain that these things don't leak. But that's not going to be a complete, not going to always offer you complete coverage, but at least some coverage in certain areas. And I think that's one of the things that we can look at. Just as I said, all of these post-quantum, or at least a lot of them, have had attacks already done. Macaleese has differential, electromagnetic, cold boot, fault injection attacks on it. Kyber has, again, differential power, simple power, electromagnetic timing, cold boot, and fault injection attacks that have been shown. NTRU has a number of attacks as well. Sabre has differential power, and masking countermeasure has been proposed as well, and electromagnetic. And there are many other ones that are newer works which I have not seen yet. So, but then again, we also can't anticipate new threats, HPC attacks, the performance counter attacks and things like that. I have not even looked at. So there are many things that we have to worry about in the future. Thank you.
Okay. So thanks, Sri, for your statement. I mean, indeed, it's an interesting debate that you raised. But yeah, I mean, at the same time, I think the concern is also that it takes a while to kind of standardize a crypto algorithm. So I think this is a constant, dilemma that will persist until unless we have more clarity about existence of quantum computers. So moving on, I mean, I think we have some time for question answers. We would kind of encourage the audience to use the Q&A feature for kind of, raising their questions. So I already see one question which has been asked by Prabuddha, which says that, what are your thoughts on runtime based timing side channel attacks on crypto modules? Have we somewhat solved this problem? Is code balancing truly effective and ideal for this? So anybody would like to kind of take on this question? Maybe Ro, would you like to go for this?
So that's actually a good question, right? To the best of my recollection, right? Code balancing, is a, how do I put this? Code balancing is an empirical mitigation, okay? And let's be very fundamental, regardless of how you apply it, okay? It's an empirical mitigation. And, in some circumstances, you can provide assurance that you have resistance. But typically, when you provide assurance, like we're talking about compliance here, right? So criteria of compliance are as good as the capabilities of an attacker. Like if you have access to higher resolution metrics, and sometimes you can have higher resolution metrics by combining many other metrics together, such as various types of counters that you can have to Ramesh's point. But the reality is that empirical mitigation do not really increase effectively the resistance of an algorithm against timing observation, unless the timing observation is such that the resolution of your counters basically gets in the noise. That's not something that you can. It depends on your recording device, really, on the quality of your recording device. So in general, you can't really provide the proof of security that comes with this type of mitigations to begin with, which means that the risk that you are susceptible to attacks is going to be higher. And in the presence of in the presence of architectures that are highly concurrent, then at that point, how do I say this? You do need to provide the proof that the code balancing is effective in any kind of concurrent situation that may occur during the execution of your architecture. And that's not necessarily something that is easy to prove. To what Apostol was saying, maybe adding some form of proof would not be a bad idea in this case, but it's something that is probably open more than being solved.
Yeah, I would like to add to that, if I can.
Sure. Yeah.
So providing libraries which are supposedly, say, constant time, that's another one. So here he calls it code balancing, but constant time. Now, one of the things is these libraries are written in, and I want to link to that, what Apostol was saying, linked to the instruction set architecture. And if tomorrow I move to a new processor, which has identically same instruction set architecture, but a different microarchitecture or a different implementation, your whole security might fall apart. And so that has to do the same as Apostol was saying, is that how do we model, right? So an instruction architecture, a set of instructions is a model on how the processor will behave. And at this moment, an instruction set architecture only covers the functionality of what this processor is going to do. And if you're lucky, it also tells how long it's going to take. And so what we're lacking is how do we model how this processor is going to behave in case there is security, right? And that's the case for instruction architecture, but that's also the same if I have libraries that I want to do pre-silicon evaluation of something's going to leak. A standard cell library, I can get out of a standard cell library what's going to be. I can estimate before I tape out how much power this chip is going to consume, because they have built models for me. I can estimate beforehand how fast this process or this ASIC or whatever I'm building is going to be. But they cannot estimate beforehand how much security leakage is going to be. It's because models are missing. I think there is a lot of work to be done on models, and that's not just for standard cell libraries, but that's also for instruction set architectures. So that's my feedback I want to give. There's quite some work to be done there.
Yeah, and also, like, I would like to kind of add on to what Ingrid mentioned is that, like, I believe that while code balancing is kind of nice to kind of alleviate some attacks, right? But at the same time, when we talk about combination of attacks, right? I mean, essentially like differential power attacks or differential attacks in general, then they may still fall apart. And it has been shown time and again that various constant time libraries can be subjected to attacks. So this brings us to the next question, which is being raised by Debapriya Basura, which says, like, the side channel countermeasures that are applied on the traditional elliptic curve cryptography are more of algorithmic nature and hence are not very expensive. For example, scalar randomization or point blinding. So the question is, like, what are our thoughts on developing countermeasures for lattice-based cryptography? Is it completely impossible? So yeah, I mean, the question is open to the panel. Maybe Sri, would you like to go ahead with the question?
My knowledge of lattice in itself is limited, but I've looked at some of the other algorithms, code-based and things like that. at least I find that there's a level of randomness inside those things, and those are going to be difficult, as far as I can see, are going to be difficult to apply sort of clear algorithmic methods, I think. So I would think it's difficult, but I think there'll be probably people who probably Ingrid might know much more about this than I would do on this. Maybe I'm passing it on.
So Professor Ingrid, would you like to comment on this question, like about the complexity of having countermeasures for lattice-based cryptography, how costly they are, and what kind of new attack surfaces they bring in compared to, say, pre-quantum circuits?
So I agree with this this person with a very difficult name, that indeed elliptic curve cryptography, you have these cool techniques as scalar randomization, point blinding, things like that, helps to some point. In lattice-based crypto, indeed there is an amount of noise. Maybe we can use that, but I think more could be done. So more could be done, but I'm not doing that myself here. So we do that in COSIC. That's these are usually questions we feed back to the mathematicians, the crypto algorithm designers to do. I don't think it's completely impossible. The two techniques that you mentioned, scalar randomization, point blinding, are very helpful against passive side channel attacks. It's not necessarily the case that they are protecting against fault attacks. So an attacker will always choose something that's the easiest way in, I would say. So that's why I think it's still unsolved problem, but there is directions that we can go. Yeah.
Especially,
if I could just add a quick note here, we haven't really played with this approach with lattice-based algorithms, but some colleagues of mine tried to apply threshold masking on those, and in some ways it was, I mean, it's not a cheap technique. Okay, threshold comes with its own overhead. It was successful, but not without major effort to make sure that the mapping of the separation of the different tiles on the silicon was successful and all that. It's very early work, so we can't really say too much about the effectiveness and robustness of this masking approach, but just to try it out and see what we're getting.
So thanks. I mean, I think moving on, because there are questions which are piling up. So, okay, so we see the next question from Avi Mendelssohn. So hi, Avi. So he asks a question on hardware reliability. So he asked that when we give up the idea for creating a reliable hardware, we can change approach to create reliable systems out of unreliable parts. Do you think we need to change our approach for protecting systems against security attacks as well? So maybe Ramesh or
yeah.
Ramesh, would you like to go comment?
It also depends on the notion of the specific security threat that you are targeting. So you can build trustworthy systems out of untrustworthy components. Especially when if your threat model is a supply chain threat where you source parts from different vendors. So if you source all, as an example, if you source all parts from a single vendor, then that exposes the threat, because one person in that where you sourced from could rogue from there could infiltrate the system. So if you want to build trustworthy systems out of untrustworthy components, one way of looking at it is diversifying or your vendor base, and that's and it's not as straightforward as that. So there's other linkages between the various interactions that happen in building these systems, but essentially as a high-level principle, I do like this notion of building secure systems out of insecure components, or trustworthy systems out of untrustworthy components, and some of that can be done based on the notion of the definition of the threat model.
Yeah, I have a different opinion on that. Actually, people, serious people who know much more about it, are looking at the opposite direction. They're trying to do, to compose systems out of secure gadgets, not insecure gadgets. That's a viable approach forward if you want to do theoretically sound assessments of security claims and all of that. If you have, and even those are problematic because they come with overhead. And once you start placing them on silicon, you have to worry a whole host of other issues. Back to the questions I was raising of how reliably can we transfer security assumptions over to silicon, all these things are in place, but that's a viable approach. Take a secure gadget, compose it with others. That's what we want to look at. I'm skeptical you can do a secure system out of insecure gadgets.
So maybe I should maybe I can clarify a little bit on here. So potentially untrustworthy, zero trust is what I mean. So when you source a component, you don't place any trust in that component. Once you place that trust, you always get disappointed unless you build it out of your own. You build the whole thing and trust yourself, right? So that's where the context of untrustworthy comes in, potentially untrustworthy. That's where my take on that is, especially when you source from,
So sorry, if I just maybe just jump in. So we've been building some systems for a while for our defense because they can't afford to build, buy extremely secure systems at certain times. So we've been getting, for example, we might just run the same program in 3 different things in different vendors' processes, and then constantly do triple modular redundancy, for example. This just basic systems that they're building within their system, just to make sure that any one of these things may not be secure, but together they might be secure. So people are doing this, but I think they're kind of specific. They're targeted towards specific problems, not a general problem. That's one of the things that we got to look at, I think.
Yeah.
May I add something?
Sure.
Yeah, may I add something? Because that's an interesting question. And actually, we came across that in the context of homomorphic encryption. So, and it goes back to some of the observation that both Ingrid and Apostol went and said earlier about modeling and things like that. And I think it's a different angle of this question. Can we build a secure system out of insecure parts? And, for example, we have been looking in research only, okay, not what we are building. In research only, we have been looking using various forms of processing in memory embodiment in collaboration with the University of California, San Diego, and to deploy homomorphic encryption at a certain scale. And then at that point, the promise is that you can achieve scale, but also much higher energy efficiency. Again, we are tackling that. Well, it turns out that some forms of memory cells are not as reliable as we would like them to be. And it opens exactly the problem of can you implement cryptography reliably and securely, so to speak, on unreliable parts? And so one of the way that we have been approaching that problem is fundamentally in looking in mathematics that have resiliency against, so it introduces some form of redundancy. For example, in the execution of homomorphic encryption, this mechanism heavily use decomposition in residue number system. And the residue number system has been actually studied in other contexts to introduce redundancy into it. And that gives you a data type that is a little bit bigger than what you would use in homomorphic encryption traditionally, but it's resilient to whatever is happening, at least statistically, not intentionally inside the hardware. Okay, which factor out, it's another aspect because until now, Ramesh was looking at, okay, if the cell is actually malicious or it can do something, what is going to happen? Now, in this case, the cell is not malicious, it's just unreliable. And so there are things. And so the approach there is, data types. Would that change the way you actually approach setting up the system security architecture? And the answer is also yes. And it's a very open problem in this moment. But again, in my lab, for example, this is a topic of forward-looking type of research.
Yeah, I mean, I would also like to add that I think the composability problem can also depend on the type of adversaries that we are looking at, like side channels versus active attacks like fault attacks, for instance. So this brings me to the next question, which is on masking. So I think this question tries to kind of ask about what is a practical recommendation for the order of masking, and also it asks about the question that whether masking can be bypassed with faults. And so it's basically asking about the combination of sidechain attack vectors and fault attack vectors. So this question has been asked by Sayandeep, and maybe Apostol, would you like to comment on this question?
Well, it is a good question, and there is no magic answer. What order of masking should you recommend? It really depends on the intended domain of your solution, how secure you want it to be, the capabilities of the attacker, what they can and cannot do, and also the cost you're prepared to pay for manufacturing a highly secure hardware, because you could do, as I said, techniques that scale up to any masking order, but they are complex, they're expensive, they come with a lot of overhead, and it's going to cost you. So there is no free lunch. People try to come up with something that is as cheap as they can afford for the purpose they need it, and also have to look at how people are going to try to abuse it, because a lot of the attack models in the literature are pretty idealistic. They're very abstract and somewhat detached from the real world, and so just because you tell an attacker to have a single point of contacting your module doesn't mean that that's the only thing they could do to it. And so it is really hard to come up with a specific masking order and say, yeah, stick for number 1 or number 2. Sorry, I can't give you a better answer, but I'm struggling with that myself.
So there is a second part of that question also about combining like sidechain attacks and fault attacks. So any comments on that?
I think if there is a contribution in the literature that really combined the two, was this contribution from Patrick Chamont and this student Naid Galati, which was called the fault intensity attack, right? Where the observation that was done there, and is a fundamental contribution, also highly misunderstood, I believe, in the literature. But what was done there is that the intensity of the fault, certain type of fault, they were kind of elongating the duty cycle of the intensity of the fault is actually proportional to the number of bits that actually to the number of bits that change when you actually write registers, and that variation can be treated as a side channel, right? And then that simplifies both side channel and fault attacks and combine that. And it was a very attractive contribution, by the way, very fundamental in my opinion. So yes, those things exist and they actually work as well for certain type of attack vectors. Again, in this case, we're talking about clock glitching.
Yep. So moving on, there is a question from Eduardo Ortega. So the question is like on fully homomorphic encryptions, and it asks like whether with the current schemes like BGB, BV, and CKKS, do we think that practical FHE is feasible? So that's, I think, $1 million question.
Yeah,
I can take it. Yeah. Okay, sure, bro.
Yeah, I can take it. So first of all, BGB, BFV, and CKKS, they are very inefficient. Like the encryption procedure is extremely inefficient and ends up in like huge data size expansion. And that's probably the main problem if you look at the problem from the point of view of computation, but there is worse than that, which is the data movement of the key material, especially when you go to large parameters that are necessary for these schemes to do something useful. Now, if you look at the objectives of the DARPA deprived program, to attain at least 4 orders of magnitude improvement in performance compared to the software on CPU, I believe, and we are performing, Ingrid can add on top of this, but reaching these orders of magnitude is possible. So while making homomorphic encryption was an aspirational goal before, I believe it's a reality now within the constraint that that DARPA, actually not I believe, it is a reality now. It's not just a belief. Within the constraints that DARPA had imposed to the system, so you can do a lot more outside those constraints. Now, is improving for respect to software and CPU for orders of magnitude brings performance to real-time performance? It depends. For smaller ring sizes, it does. For medium ring sizes, so if you do bootstrapping, it does not. But this is something that if I were to answer this question, let's say a few years ago, there was not really a technical path to that, so there was nothing really in sight. Now, if I would take the system that we are building from DARPA and remove some of the constraints and build, a larger system, then I think we can make that. Nonetheless, modern homomorphic encryption is homomorphic encryption on polynomial rings, and anything that comes from theory to make the schema more efficient becomes a multiplying factor on the hardware. So I see a line of sight that can happen. Perhaps not really in BGP or CKKS, but with something that is, let's say, what they call the 4th generation, which I think has many interesting aspects to it. So yeah.
So I can add one, one line on that. It also depends on the target application. If you look at the DARPA DeepRive project, they are just looking at inferencing on data, machine learning, right? If you open it up to other applications, again, then all of a sudden the goalpost moves further down. So
yes and no, Ramesh.
Progress.
Don't underestimate the goal of the DARPA deprived program, because the goal actually is really to enable what the people dub as bootstrapping, which is largely not used today. And even something as simple as inference of things like that, when you put bootstrapping, among the mechanisms that have been cited here, BGP, BFV, and CKKS. CKKS has the advantage that provides you the largest capacity for a certain ring size. You can do something in BGP as well, but CKKS, and if you do bootstrapping on a relatively toy neural network with toy dataset on 112 CPU, you still take about 4 hours per inference. So it's not about, so when you introduce actually bootstrapping into the problem, everyone believes that the component of complexity is the complexity of the ring arithmetic on lattices. Well, that's the efficient part of it, by the way, because we can implement that very efficiently. The actual complexity are the procedures to manage the ciphertext growth and the noise growth. Yeah. So there where is the actual problem in homomorphic encryption. So even something simple, if you want to do high precision, which means that you need to do bootstrapping, and the real value proposition of the DARPA deprived program is really enable security, high precision, and performance. Yeah. So that is,
So there are also some attacks, right, which are published against CKKS, partly because it tries to exploit the approximations which are there, right? So yeah. So in a sense, right, when you are doing less bootstrapping, or you are like introducing error, then that also brings opportunities for other class of attacks, probably, right? I mean.
Yeah, so, well, first of all, there is no practical construction of an homomorphic encryption scheme that is resistant to active attacks. So that's the first thing. The issue with the CKKS, and it is a real issue because it's a passive attack. Mm-hmm. So that's the real thing. But it also depends on the deployment model. If you're looking to typical outsourcing, then CKKS is secure. If you are looking about sharing the decryption with the third party, then CKKS is not secure anymore because you don't trust something in the middle. So it's more about that than the mathematics per se. In the traditional outsourcing model, where you outsource the encrypted data and the function to an untrusted party, and then you get back the result, you decrypt it, and you keep it for yourself, then CKKS is fine.
So moving on, okay, so the next question that is in line from Bhuvnesh is on like the application of in-memory computation. So I think, Ro, you mentioned about the memory complexity of FHE. So maybe it's in line with that, like in-memory computation as a possible solution to hardware-based accelerators for PQC schemes. So the question is open to the panel.
Right. So the reason because it's important to look. Okay, if you do an architecture for a block cipher, for example, and it's an architecture with let's say a specialization of an instruction set of a processor or things like that, you soon realize that actually you don't need the cache because everything is contained and things like that. As you move to things that are more complex, you actually need a memory hierarchy that is more or less efficient. And the way we are looking at is really what is the architecture that promises us to have the largest gain in terms of energy efficiency. And that's why we are looking into that. If I have to tell you, have we done side channel or things like, no, we have not, right? It's just an architectural exploration at this point. So I don't have, there will certainly, because that's more of a, but I cannot tell you how I would attack this system from that perspective.
Right. So I think we are also running out of time, and while the questions are, kind of piling up, I would think that it's time to wrap up. I mean, we would probably try to answer some of these questions after the presentation. So maybe a quick word of, final comments from the panelists would be welcome. So maybe we can have, start with Professor Ingrid, like any final concluding comments?
Yeah, I'm always first one to be put on spot. So yes, I think we touched on many problems. I think if you want interesting research problems, not just for post-quantum crypto or for FHE, is about models. I think that's what I really agree with Apostol there. The second thing is for post-quantum crypto, I also agree with Sri that actual implementation, sometimes people say post-quantum is nice exercise for the mathematicians to have a new target for designing crypto, but the implementation aspects are costly. So I had prepared for last week was Eurocrypt, some numbers there, the cost of masking and higher order masking of lattice-based schemes. It's really factors, right? So, and then yes, the third problem, we really enjoy the FHE project, the DARPA deep dive. We're in a competing team to Ro. And there, the challenges for FHE, I'm not so worried yet about the passive attacks somewhere in the cloud, but the challenge is really the memory management, data communication issues, things like that. I think the arithmetic is pretty much under control. And for all these algorithms, I think it really requires close collaborations with the crypto guys. So if we can tell them, look, we need a hash function, and the same problem occurs for hash functions. We need a hash function that's easy to mask. Or we need a lightweight crypto algorithm which doesn't like blow up if I try to do a threshold implementation of it. These are the kind of collaborations that we have and that we can do by giving them models, because I think some of these models that they are using is very, very primitive, and they need these primitive models because otherwise they cannot reason, they cannot do formal reasoning. But I think there's quite some collaboration is possible there to really make progress.
Thanks. Thank you. So maybe Ramesh, would you like to comment anything?
Yeah, provable security is like a X mark on the back of whatever that product is. So I think those things will be broken easily. So there is nothing like provable security, especially once you start implementing. Provables implementations are again a myth. Of course, we should aspire for those. We should come up with all of these things of verifiable security implementations, verifiable, provable guarantees against side channels. Pick a favorite side channel. All of the, even if cost is not even taking away the cost investment, or I don't see these as cost, I see them as security investments. I see the positive. If you ask for something difficult, you got to pay for it. So it's a security investment. So even if you have unlimited investments, I think some of these goals are aspirational, which is always good to have, because especially for security, for power and timing and so on, at some point it becomes manageable. But for security, maybe I'm proven wrong, but that's the fun reason why security is so much fun. When somebody says it's provably secure, and if you go and read papers, there are a bunch of provably secure papers, by the way. Maybe I have one of them too, I don't know. So all of them have been broken, FYI.
No, provable security works as long as you stay within the model that the person who wrote the proof is working with. The nice thing is an attacker just goes outside the model and it's gone, right?
Yeah.
That's the thing.
There is a famous saying.
That's where the problem.
There's a famous saying which says like, what is probably secured is probably not, but maybe that is a little far-fetched. Yeah, so maybe I'd request Sri to make some comments.
Thank you. So I think, as Ingrid said, modeling is deeply important. I think we also need to worry about analysis of all the different types of attacks and how to implement these things. And I think third thing is every time we optimize something, particularly in processes, that's often a surface for attacks. Optimization is probably, let's start with caches, for example, and then branch predictors, etc. So many levels of optimizations are surfaces for attacks, and we got to watch out how we go about optimizing things from now on when we do security. And I'll leave it at that. Others have covered a lot of the other important things.
Apostol, would you like to go ahead quickly?
Sure. I mean, it was a very enlightening discussion. It is nice to see that some of the points around modeling and provable security and all of that resonated with at least a few of the panelists. That's really good. Look, crypto is one of these domains where theory matters, but practice matters as well. And my point is that in engineering, traditionally, people have restricted themselves around things that are closely related to business, such as power, area of your silicon, throughput, all of these things. We haven't figured out ways to map security into that. And that's the whole, my point is, let's go a little bit on the edge of the envelope and think about ways to formalize our notion of what's secure in practice. I agree that the models in theory are important, but how do we translate these things in practice? That's the key. And it may not be perfect. It may never, ever be perfect, but I'm sure we can do better than what we're doing today if we try.
Yeah, that's a very good point. So finally, Ro, would you like to make some comments? Yeah.
Yes. So following the Apostol and what others said, conclude. Once the model are in place, the next step is really assurance, right? So how do you apply them in practice, and how do you quantify the risk that things, and that comes into the provable security things, that within a certain context, things are actually secure as soon as you move from that context. But that is a matter of practices, like, it's a matter of assurance. Within Intel, for example, we take security very seriously. to the point that there is a whole process that if your checklist in the assurance process doesn't check, thing gets delayed or never find the light of anything. And the assurance process is very rigorous. It also includes the cryptography, but it includes the system security as well. But for what concerns assurance in cryptography, going back to first order mitigation, second order mitigation, and things like that, right? So in part, there is this cat and mouse race that says, okay, the capability of the attacker. But when you go from first order to second order, the complexity of the attack actually greatly increases, which means that the risk of being attacked really depends on how fast the technology progresses in your attack setup. So if you can be ahead of that game, and that doesn't ensure system security, by the way. So in some contexts, the assurance can be quantified very well. It might be more costly than others. That's a different story. But again, I think moving toward more formally proven system, and then the assurance process to be built around that. That's what we are doing at Intel for lattice cryptography, for example. Or we are preparing, right? Because for now, the platform had made the space with the largest innovation to support lattice cryptography. And other things will come, but then, how do you evaluate it in your secure development life cycle? That's the assurance part that we're thinking. So interesting problem, a lot of investment. Intel invests a lot in research. Only Intel Labs invests around $50 million per year. Not only in security, globally, speaking in research. So, and we work with academics worldwide. We learn from them, transfer from them. We also contribute to the research, and this conduct needs to go on, but it also needs to be intertangled with this assurance process to quantify things in practice.
So yeah, I think we are already running out of time. So thanks for these nice comments. And one thing is for sure, we are going to stay busy. So we have got lots of interesting problems ahead of us and interesting solutions to look forward to. So with this, I would like to hand over to the organizers and maybe Swaroop or Yer, and you can take it over.